Okay, hi students. So this will be the final video for this course, and we'll have some important points for you to actually take note. So we have last finished with the decision tree, which is the last algorithm that we saw under supervised learning, where we have a target label that we actually want to do prediction. So now we are actually going to look at the unsupervised learning. So this is where unsupervised learning is where you're not interested in predicting. You're actually more interested in finding the patterns in the given data. So that's why for this kind of techniques, for unsupervised, the input data is not labeled. That means there is no data that has a corresponding output labels that you want to predict. So the aim of this unsupervised algorithm is actually to discover patterns and structures within the data. So if you want to make some prediction, then you use supervised learning. If you want to find the patterns or structures, then you use unsupervised learning. So this is the important point for you to actually take note. So the first one is you can see the difference between supervised and unsupervised. So supervised is like on the left. So you can see that there is a difference between supervised learning and unsupervised. Like for example, in the supervised learning, there's two-dimensional data points that are drawn along with the classes that they belong to, which is red and also blue. So the learning model is to find the line that separates these two classes the best. So you can see that under supervised, you try to find the model that able to do this kind of classification. But in unsupervised learning, we known as clustering. So in unsupervised learning, the same two-dimensional data points are drawn, but it's not they don't have any labels. So the aim of the unsupervised is actually to find the patterns that are present and based on the similarity between data points. So here you can see there are two different clusters and it detects the cluster. So you can see this one, you try to find a line which can separate the two classes, which is to classify. In unsupervised, it tries to find the similarity between the data points and it forms clusters. So this is, you try to find some kind of patterns here. So this is one example of difference between supervised and unsupervised. So there are two major types of unsupervised. The first one is clustering, grouping of the data, and also dimensionality reduction. So we'll look at the clustering first. So for the clustering, the idea is what? To divide or group the data into several categories based on their similarities. So let's say you have this particular, let me see this data, this screen is a bit small, yeah. So let us assume you only have two features in the given data set. That means y-axis and x-axis. The labels of the data is not given. So when we actually plot the data, it looks like this. So the left-hand side of the figure shows the data without label. I mean, there's no particular label. And the right-hand side here represent the clustered data based on the similarities between the data points. I mean, you can see the more density between, there's some similarity between these data points, some similarity between these data points, and some similarity between these data points. And it forms a cluster. Then how it forms a cluster, we will see in the next one. So to test an unsupervised learning algorithm such as clustering, we actually give an input that is to be predicted. The learn or the trained model checks the test input against every cluster. So this is when you test an unsupervised learning algorithm, like for example clustering. And if you are giving an input, and based on the input, based on the unsupervised learning model, what it will do is the learned or trained model, you'll just try to check the test inputs and try to see that particular input, is it closer to cluster number 1, cluster number 2, cluster number 3, and whichever that is closest to it, it will actually label it at that particular cluster. So that's why the input test observation is assigned to the cluster that the point is more similar to. This is how you actually form clustering. So one very, very famous popular clustering algorithm is k-means. Okay. So k-means is very, very popular. It's actually an iterative algorithm, which means it runs on every cycle, iterative. So the aim is to find the best cluster for each observation in every iteration. So this is the first step. These are not the first step. These are the steps followed by the k-means algorithm. So first, we actually choose a desired number of cluster. So that is actually represented by the value of k. So k means k is actually the number of cluster. And input this number k to the algorithm as an argument. So of course, obviously, the number of clusters has to be more than one, right? Minimum must be 2. Second, the k input data points are assigned randomly to k clusters. So let's say if we have 2 clusters, you choose 2 clusters. The input data points are assigned randomly to these 2 clusters. And these 2 cluster points become the centroid or center point of the clusters. And third, the distance of every data point is calculated from the k centroids. Every data point is assigned to that cluster whose centroid is closest to it. Fourth, the centroids are recomputed for all the clusters because the data points are reassigned to the clusters. So I think I have a, let me see if I have a diagram. Okay, we will see this cluster when we actually do the coding part. So this time the codes, try to make it short. We will be using this iris dataset that we already have it. So we'll import all those and we'll try to look at the top 5 data of this iris dataset. So you have to make sure that you keep the iris dataset in the same working directory. Okay, so you can see how the data frame looks like. To find the optimum number of classification, so earlier remember that when you want to form basically why we actually using this particular iris dataset, we have actually used this for supervised learning, right? To predict the species based on the input variables. We have done that before, but now we are going to use the same dataset, but we're going to see whether when we use unsupervised, which is the k-means clustering, are we also getting, because the species, there are 3 species, right? Are we able to get 3 distinct cluster? So one of the first thing of the k-means algorithm is choosing the number of desired clusters. So how do you know what is the best number of clusters for the k-means? How do you select the k value? So this is very, very important. Please kindly take note that how do you select the k value for k-means is very, very important, this slide. So to find the optimum number of clusters for classification, we actually implement a widely used technique which is known as the elbow method. So we plot within cluster sum of squares against the number of clusters into line graph, allowing us to observe the elbow of the graph. So within the cluster sum of squares, it means you actually, let's say you have the data and you're forming 2 clusters, and within that clusters you are trying to find the sum of squares. So sum of squares means the distance, equivalent distance between each point within the cluster. And we try to plot it against the number of clusters into a line graph, allowing us to observe the elbow. So take note that the elbow method is the way that is used for selecting the k for the k-means clustering. Okay, so k, take note that the k is actually refers to the number of clusters, and we are using the within the sum of squares, which is actually the sum of square distance between each members of the cluster and also its centroid. So these are some of the important points that you have to take note. So this one is, we're trying to have this elbow method on the iris dataset to pick the optimum number of clusters. So we're going to import the k-means and we're going to create an empty array which is within the cluster sum of squares, and we are trying to get the features from the data set. So you can see that all the rows from the iris data location, and also 1, 2, 3, 4. So we are not taking the ID, the 0, so we're leaving that. We're taking 1, 2, sorry, 1, column 1, 2, 3, 4. Is that okay? We're taking those 4, all those values. So dot values, we're taking that. And what we're trying to do is within the range. So this one for I in range 1 to 6 means that this is actually referring to the K value. From I to 6 means is from 1 to 6 means it is actually 1 to 5. So what you're doing, you are trying to plot with the K value 1, 2, 3, 4, 5. So you see the and this is the K means, which is the from the scikit-learn, which is we are using the K means. So it function which requires the number of clusters. So you are providing that I, you're trying to plot, try to get what is the K means value that you get when you choose cluster 1, 2, 3, 4, 5, and you try to fit into the model with the X values and try to get the K means inertia value. So this is actually the within the cluster sum of squares, and we try to plot within the range 1 to 6 with respect to the within the cluster sum of squares value, and then we plot. So when you plot this graph, just found some error, let me check. Okay, I managed to find what is the issue. Earlier when we actually something wrong with this K means fit function, where earlier we actually set it as cluster 1, right? So that cluster 1 it doesn't accept it as an input, so we have to start from cluster 2 to 6. So I made some changes here, cluster 2 to 6, and then we're able to plot. So this is the number of clusters versus the within cluster sum of squares. So the elbow method, it actually this graph, it doesn't show it very clearly, but the elbow, when you actually have one cluster, single cluster, then only you'll be able to see the elbows very clearly. So it looks like your elbow, right? So that's what we know as the elbow method. So the elbow method, it gives the optimal number of cluster where the elbow occurs on this plot. So where is that elbow? The elbow is the point after which the WCSS doesn't decrease significantly. So you can see here it decreased significantly, right? Then after that it decreases some more, and then it decreases some more. So by right, the optimum number of cluster is 3, where it doesn't decrease that much. Actually, you may ask also, this 4 also looks like less steep compared to 3, but it is much more clearly, you'll be able to see if we are able to plot from 1 number of clusters. So either is when you actually plot from 1, but somehow or other this is not accepting that 1. So I think the libraries, when they update, then have such issues. So but when you plot from 1, you'll be able to see that the point number 3 is where it has the minimum, it doesn't decrease significantly with the increasing number of clusters. So but when you actually plot from 1, you'll be able to see, here it's a bit confusing because it seems like 4 cluster has lesser does not decrease significantly, right? But here also you can see this is, it decreased significantly, and after 0.3 it doesn't decrease significantly. So this is your elbow point, from a decrease significant, and it doesn't decrease significantly. So this is the candidate or the optimal number of clusters. So this is how, and also if when we actually use this on the iris, we also know that the iris has three species, right? So take note that is how to select the K for the K-means using the Elmo method. This is very, very important. Then of course, maybe for this one, I can go here. So let's say if you want to apply the K-means. So now after we use the elbow method, then we can specify the number of clusters. And this is the initialization. The K-means, we just use the default K-means. The iteration is the number of iteration that you want it to run. Initial N, the clusters, initial clusters, you can actually set any values. 10 random state set at 0. And we supply in the X value to try to find in create that the K-means classifier. This is actually creating the K-means classifier. When you actually provide X, you can actually find which cluster it actually belongs to. Right, so let's try to run this. And then we can actually try to visualize the cluster 0 and 1, which is sepal length cm versus sepal width cm. And then when we actually try to plot this, so you can see that there are three clusters, which is the blue one, and then the red, and also the green. And the yellow is the centroid point of the red. This yellow is the centroid, the center point of this cluster. This yellow is the center point for this red, and this one is the center point for the green. So likewise, we can also visualize the cluster 2 and 3. So this is earlier it was the sepal length and sepal width, right? Not so apparently, not clearly you can actually see. But then from the petal length and petal width, you can actually see some clear kind of clustering. So you can be observed that the K-means managed to actually identify the three clusters. Of course, identify three clusters because we provide the argument 3 clusters. And how do we got it? It's from the elbow method. So one of the clusters that we actually arbitrarily name as the iris second is, you can see, separable from the iris first, which is this one, right? It's really clearly it's distinct from the others. So you can see that linearly separable. That means linearly separable means you can actually have a line to actually separate from these two. And with respect to the iris first and iris third, when actually we plot petal length versus petal width. Since we are just using the features without the output labels, we do not know the labels of the iris species yet. Here you're just labeling it as the first, second or third. We didn't label the species yet. So to visually assess the clustering capability K-means, we can actually draw the scatter plot of petal length versus petal width for all the 3 classes using their given labels now. So now you can actually assign the given labels Sentosa, versicolor and virginica. And now if you try to plot this, the same thing, but now you can see that yes, iris Sentosa is a separate group. This is the versicolor and virginica. So they all have a distinct petal width and petal length for each one of these species, right? So what is the conclusion for the K-means? So from the K-means cluster, we can actually reveal that iris Sentosa corresponds to the iris second, and of course it's linearly separable for the 2 species of the data set. And on top of that, you can also note that the versicolor and virginica are not that much separable in this plot. They are quite close. So the output of this clustering shows some example points that are erroneously assigned to the wrong cluster because the training examples of the 2 and 3 classes are mixed with each other. So thus, when the 2 different classes are mixed together, the result of the clustering, it can actually show some error. So that is on the clustering and what are the important things that you need to know for the clustering k-means that is there. Now the another technique of unsupervised is known as the dimensionality reduction. So dimensional reduction, the aim is to reduce the number of dimension in a given data set. So what it means by reduce the number of dimension means is referring to the columns, not rows. So if you have a lot of columns with it bits, you have a lot of attributes, a lot of input features. So that increases the dimension. But you can also use the dimensionality reduction approach to reduce it. So in data science, I think this is what I mentioned. The dimensionality refers to the number of feature variables. The lesser and the distinct feature you have, the lesser computations that you have to perform on training and testing your machine learning model. So some of the key benefits of applying dimensionality reduction technique to a data set includes the following. So this is important. What is the key data set? So some of the benefits, computer memory is actually reduced when the dimension is reduced, and fewer computation is required, and fast training can be done on a smaller number of dimension. And visualizing data in high dimension is very, very difficult because there are a lot of attributes, and therefore when you actually reduce the dimension into 2 dimension or just 3 dimension, it allows you to actually plot and observe patterns. So these are some of the things on the dimensionality reduction benefits. So let's say, for example, dimensionality reduction methods remove redundant features by paying attention to the dependency and correlation of features. For example, let's say if you have 2 variables, time spent on treadmill in minutes and the calories burned. So if you notice that these 2 variables, they are highly correlated, as the more time that you work on a treadmill, of course naturally the more calories you will burn. So therefore there is no need to actually store both variables. Just working by one of it is actually sufficient. So when you apply a dimensionality reduction technique to a data set of 3 features only, and you may project the 3D data onto a 2-dimension plane. So this very effectively reduces the number of points and the number of computations. So there are 2 ways that you can actually do the dimensionality reduction. The first one is just select the most relevant feature from the original data set. This one we have done before, right? Known as the feature selection. We actually did the correlation matrix and we try to find out which features have some correlation with the target variable. So we have actually done this before. And another one is for find a smaller set of new variables as a combination of the input features. Now this is important, which is known as the principal component analysis. What principal, this is known as the feature extraction. I mean, earlier one, feature selection is you just select the feature. So you may have like 10 features, out of it you may select like 7. So you extract them out. Another way is known as the feature extraction, and this one, it actually creates a new sets of smaller sets of new variables, which is a combination of all the input features. So this is known as the feature extraction, and this is very, very important for you to know what is principal component analysis. So this is the feature extraction is known as. So what does principal component analysis do? It actually creates new features by linearly combining the existing features. So let's say you have like 10 features. What principal component analysis will do, it will extract all those features and maybe you'll just have new 3 new features. But these 3 new features has the features of all those 10. So this is the feature extraction. It extracts the important features of all these existing features. So the newly extracted features are known as the principal component. That's why the name comes, principal component, which aims to retain the maximum variance in the given data set. That means using the principal component analysis as part of dimensional reduction. Let's say if you have like 10 features, but PCA will create 3 new features, but these 3 new features has all those components of the 10 features. So when you want to train your model, you only need to use these 3 features. So all these are important. The principal component extracts in a way, not this slide. This one is important to know what is PCA and what is the aim of PCA. So principal component, it actually extracts all the components, the features in such a way that the first principal component explains the maximum variance in the data set. So let's say, like for example, you have the 10 features, but then it creates the first 3 features. The first feature will have the maximum variance of the 10 features, and then you have the second principle will explain the remaining variance, and the third will whichever is not covered by the first 2 variants is covered in the third one. This explanation is not so much required for you to actually understand. So what you need to understand up to this point is, because we are not going into the depth of how the principal component analysis is being derived. What the concept that you need to understand up to this point is, principal component analysis is part of dimensionality reduction technique, which is known as the feature extraction. That is the principal component analysis, right? It creates a new set of variables, which is a combination of all the input features. Okay, so just on another note, this is also quite important. Why, where, what kind of data sets or problems that you want to use the PCA for. Of course, as I mentioned earlier, the PCA, this is important, very important. PCA, of course, as I mentioned earlier, it is used for dimensionality reduction. You want to actually reduce the size, reduce the required memory, so that you can actually speed up the algorithm, right? Remember, we've seen the benefits of dimensionality reduction. So all this applies to PCA. The benefits, any data sets that has a large data set, you want to use the PCA so that you can reduce the data size, you can reduce the computation time, so that the algorithm will be able to execute fast. And also in terms of visualization, it's easier for you to actually visualize. So these are some of the important points that you need to take note here. So here's an example. So we're going to use the PCA algorithm. So we're going to import the model, and we're going to use it on a handwritten digit recognition data set. So you don't have to download this. Sorry, this is some of the links that you can actually get it. Hold on, I've not uploaded this file. Just hold on. Okay, so this is I've uploaded the files in the same directory. So we're going to define a variable train, and we're going to read the CSV file, and we're going to create a data frame using the pandas library, and we're going to pass the values that we actually have actually extracted out. So we are going to have we're going to create a new from the train label. We're going to create a data frame label, and what we're going to do is we are going to import the PCA, and we're just going to randomly select the number of components as 50 and try to see what is the results from the PCA. Okay, let's see. And let's try to plot. Okay, have to define the np import numpy as p, and run this again, and let's run this again. Okay, so here we have a plot. Okay, so what this plot actually shows is the component wise and also the cumulative explained variance. So this data set, this handwritten recognition, it actually has 60,000 observations, which means 60,000 rows, and also 785 features, 785 columns. So you can see that the graph here, the blue line actually represents the component wise explained variance, whereas the orange is represent the cumulative, which is what is extracted out of the PCA. PCA extracts this. All right. So look at the orange line. Look at the orange line. So what this actually shows is that this is the number of PCA components that you actually use. PCA number of PCA components that you actually use. You can see that when you are using 10 components, 10 components means 10 features. 10 features. Remember that this data set has 785 features. But when you use the PCA, just by using 10 features, you are able to extract around 50% variance of the original data set by just using 10 components only. So 10 components means 10 features with respect to 785. If we use 50 features, you are able to get 80%. You are able to represent 80% of the entire 785 data sets features. So what this actually means is that this is the power of the PCA. So just by using 80%, you are able to just by using the 50 PCA components, we are able to get about 80% of the variance of the data. So which means what? Instead of using 785 features, if we transform them using the PCA and use the new features, which is the principal components, we get about 80% of the variance in the data set. So let's say in terms of calculation, the use of 50 features instead of 700 means we use 50 out of 785, only 6.4% of the data, and that saves us about 96.6% of the computation. So this is really the power of the PCA. So take note the PCA, you need to know what the PCA is and for what kind of problems that you want to actually use, where or when you want to use the PCA, right? So evaluating performance of the trained model. So some of it we have actually already gone through. So the model evaluation aims to estimate the generalization accuracy, right, of the learning model on the future or unseen data set. So the methods for assessing the performance are divided into two categories: holdout and cross-validation. We have actually touched on the cross-validation right before. And take note that the cross-validation is very, very important. You need to actually know what is cross-validation, and you need to be able to explain the importance of cross-validation. So that is very, very important. So both this method uses a test set to evaluate. That means it splits the data. It's not a very good practice to use the training data to evaluate the build model, right? Because why? The model is actually remembers the training data very well, and if you test using the training data, and of course it will perform very well. So however, it may not generalize to unseen test set. So that's why we want to split into the training and also test set, right? So let's see on the first one is the holdout method. So in the holdout method, how the splitting is done is the data set is randomly divided into three subsets. The training sets, which is used to prepare the model. The validation set is used to assess the performance of the model, which is built in the training phase. By validating, then you can actually fine tune. And then you use that test set to assess the future performance of a model. The holdout looks like simple and flexible, but the differences in the training and test data sets can result in changes in the estimate of the model accuracy. So this is one of the setbacks of using the holdout method. Now, cross-validation, remember that cross-validation is important. You need to know what is cross-validation and the importance of it. We often choose a percentage, right, of the training set. Earlier in our linear regressions and things like that, we set, or the decision tree, naive Bayes, we set 75%, 25%, right? So that's what we are using on the cross-validation. So if the model is iteratively trained and validated on different validation sets generated randomly from the training set, then the process is referred to as cross-validation. So one of the most commonly used technique is the k-fold cross-validation, where the original data set is partitioned into k equal size of subsets of fold. So let's say you have a whole data set, then you segregate them into 10 equal size subsets of fold. So from each subset you are just taking. So typical value of user specified number k is between 5 to 10. So please do not get confused in this k and also the k means k value. Cross validation k is referring to the subsets or the folds. K means is the number of clusters in the k means. And this process is repeated k times such that each time of the k subset is used for a validation set, and the other k minus 1 subset are put together to form the training set. So this is one of the best technique to make sure that cross-validation, to make sure that your data, your model gets trained over across all the data set. So in the first iteration of the process, the cross-validation uses, you don't have to know all this in great detail. For cross-validation, you just need to know what is it and why is it important. So it uses the training set to generate a validation set. In the next iteration, what it does, it generates another validation set from the same training set, and the process continues. So the benefit is it increases the robustness of the training model and is used to tune the parameters of the model, which means this helps us to get the most optimized model. So this is where the importance of CV comes in, cross-validation. So this is a figure. This is change something here. So you can see how the original data set is here and is split into training and also testing, right? So now the cross-validation is done on the training data set. So let's say here you choose k value of 10. So what it does, it takes the k value, then it splits into 10, right? So in the process of cross-validation, what you actually are doing is we repeatedly train the model on 9 out of the 10 parts and test the model on the left out parts. So you train and then test on the rest. So, and you do it for each time. You take the first one to train the model and then you test on the remaining one. So like the cross-validation, you train your model 9 out of 10. That means you take this 9, let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? you take nine parts of the training set to train, and then use the remaining one to test, and then you repeat. You take 9 also, but maybe now you take from this 9, and you test on the remaining one. Then the next one, maybe you take this 2 and this 7. Then you leave out 1. The rest you use for training, and the 1 you use for testing. Then you move. You leave out this one, you take this 3 and all this thing 6 here. You train and test on this. So like this, you'll keep on iterate for all the part. So this is how the cross validation is being done. So cross validation is a single parameter, which is K, that represents the number of groups that the data to be split. So that's why it is called as the K-fold cross validation. So if you use K value as 10, then it becomes a 10-fold cross validation. So here's an example of the cross validation. So we are going to import NumPy array, and also from the model selection we are going to use the K-fold. We're going to create a random data sample, and you're going to prepare the cross validation. You're going to just use a 3-fold, and you're going to try to print those data sets. So it'll run 3 times, right? Oops. Sorry, let me see what's the issue here again. So I just remove the true, just allow it to just have this number of cross validation. So you can see that from this value, so you can see from the output is what happens, that we actually have split our data sets. You can see this is the training data set. This is a small number only, right? 1 to 6. Now it actually splits. It actually splits into 3 distinct training and test data sets. It's not the same at all. You can see the train and also the test. So this is an example of the cross validation. So this is what I just mentioned. So we can actually train our model on all these 3 training data sets, and then we can actually assess from all these 3 training data sets, and the performance is actually nothing but an average is given on the summary of the model performance. So when we said about the model evaluation metrics, we have already covered some part of this before. So some metrics are required to quantify the performance of the trained model. So of course it depends on the given task, right? For example, if you're doing classification, regression, and also clustering, most of the time we can see that we use classifications and also regression. So see, some of the metrics that are used in classification and regressions are as follows: classification accuracy, confusion metrics, precision recall curve, and ROC, which is known as a receiver operating characteristics curve. So we will see this soon. So classification accuracy means how accurately for classification problems, how we define is the accuracy, right? So what is the number of correct predictions that is made as a ratio of all prediction that is made. We will see that on the classification accuracy in terms of the confusion metrics. So this is very, very important. So confusion metrics is very, very important. I think in a later point of time we'll have a simple calculation on how do we actually find the accuracy. You need to know how to identify the true positive, false negatives, false positives, true negatives. We will see in detail on this confusion metrics, and you should know how to extract those information out and apply in the formula to find the accuracy for the confusion metrics. So that is very, very important. So what a sample confusion metric is shown here before. So this is the actual class. So let's say this is for classification. So let's say if it's let's say if you're taking a particular thing, whether it's going to rain or it's not going to rain. So positive means yes, it's going to rain. No means it's not going to rain. So this is the predicted. Actual yes is going to rain. Actual no is not going to rain. Of course, the input features could be, weather, date, and the wind, and all these things. But we are looking at the predicted class, right? So actual means actual, yes, it's rain, no, it's not raining. And predicted class positive and negative means how many times it predicted the true positive correctly, which means the actual data shows that it rained, and also the model able to predict correctly, yes, it's rain. That is known as the true positive. What is false negative? Actually, it rained, but the model say that no, it didn't rain. It predicted no rain. So that is the false negative. And if you look at the actual class, no, it's not raining. How many times it equals to true negative? True negative means yes, correct. It's not raining, and the model able to correctly predict yes, it didn't rain. But what is false positive? False positive means it falsely giving by right it didn't rain, but the model predict it as if predicted that it's going to rain. So that is false positive. So you can see the diagonal one is the correct one, which means yes, it's supposed to rain and it correctly predicted it's supposed to rain. No, it's not supposed to rain and it correctly predicted no, it's not going to rain. So false negative means it's raining but it predicted no. False positive means it's not raining but it predicted it's going to rain. So this is how to read the confusion matrix. So what I mentioned, the diagonal element indicate the number of points that for which the predicted label is equal to the true label. That's what I mentioned, the diagonal, right? While the off diagonal is they are the misclassified or wrongly labeled by our classification model. So the diagonal one, this one, this and this. These are the correctly predicted, and the off one, off diagonal is this is falsely classified, these two. So that is the confusion matrix. So that means the higher diagonal values in the confusion matrix, the better, which indicates there are many correct predictions. So we'll go into the detail in the next topic. So which means the value of the true positive should be high, true negative should be high. This one by right should be 0 and should be 0, or should be minimal. Then only model is the high will have high accuracy. So area under the curve AUC, it actually measures the discriminative ability of the binary classifier. Binary classifier, yes, no, it's a binary classifier. The ability, so this shows the ability for it to differentiate between the positive ones and also negative classes. So in this case, let me just minimize it a bit. So this orange line is actually the area under the curve, under this curve. But right, the higher the value, the better is the ability for it to discriminate. So the lesser it is poorly, it actually performs poorly. So a perfect classifier will have 100% area under the curve. It will reach almost 100%, but you know, that's an ideal case. But the higher the value, that means more area under the curve. When it's more, then it has a better discriminative ability. So the performance of the classifier decreases if the area under its curve decreases. So these are the things that you need to take note. So of course on the regression metrics we have already seen this before. I've already sent the video. So I won't be covering this back again, but I did mention that the regression metrics are important. Okay, so that's it. So we'll continue with the last segment, which is on the interpretation and reporting of findings. So of course, after we have done all this modeling and things like that, we need to look at how we want to interpret. So we should interpret the result using suitable mathematical and visualization tools. So now we're going to learn how to explain certain findings. What are tools that you actually want to use? So as I mentioned earlier, the confusion matrix. So this is very important, confusion matrix. You're going to see at how you want to do the calculation to do the accuracy. So this is very, very important. So in a binary classification problem, we call one class positive and the other class negative. There are 4 types of outcomes. One is true positive, which I just mentioned earlier, that when the model correctly predicts. The true negative means this is an outcome when the model correctly predicts the negative class. False positive means the outcome when the model incorrectly predicts the positive class. And also false negative is an outcome when the model incorrectly predicts the negative class. So let's say, for example, we use this is the famous story, the boy who actually cried wolf. So let's say we make this definition, and the shepherd says wolf. So let us define this as positive class, and no wolf, that's negative class. So we can summarize the outcome of this prediction model using a 2x2 confusion matrix, which describes all 4 possible outcomes. So this is the example. Let me just try to make it bigger. So true positive means what? The reality is a wolf came, and the shepherd said also yes, a wolf came. False positive means what? The shepherd said wolf, but in actual there's no wolf. So this is false positive. False negative, let's look at the true negative. Remember, the true positive and true negative is what we are really concerned for. True negative means the shepherd said no wolf, and in reality, yes, there was no wolf. But what is false negative? The shepherd said no wolf, but actually a wolf came. So these are the 4 possible outcomes, as I have shown you earlier also. So this is how an example of a confusion matrix is being represented, right? So let's say this one, let's look at this problem as, now we just try to change the position of the true and actually false, right? So you can define however you want also. So let's say the actual no, actual yes, right? So take note that not necessarily, because in our earlier example we saw that, you know, true positive must be on top, negative must be below. It's not necessarily in that order. So let's say here purposely we have like actual no and yes, right? So which means actual no means, and this is the actual no, true no, right? True no, true negative, not true no, sorry. It's true negative, right? This is just for the sake of you and trying to understand, not necessarily yes must be always on top. If yes is on top, then what this one will be? This will be predicted yes, so which means this will be true positive, right? So it can be any way also. But look at this matrix, you'll have the actual value always will be on this side, and the predicted will always will be on the top, right? So you always need to look at the diagonal part. So the actual no and predicted no. So it's predicted 50, but actually it's no, but wrongly predicted yes is 10. So 60 examples. So this data set has a total of 165 examples or 165 rows, out of which there are actually 60 no's. This value 60 is the actual no total value. By right, if your model is good, it should be able to predict the true negative as 60 and false positive is supposed to be 0. But here it only able to correctly predict 50 but wrongly predicted 10. The actual yes, how many out of the actual yes total data set is 105, and only 100 times able to correctly predict as true. And false negative, it have 5 times it actually given a false prediction, that is negative. So you need to know, you need to be able to identify which is true positive, which is true negative, false positive and false negative. Remember that true negative is when it's supposed to be negative and it correctly predicted negative. True positive is when it is actually positive and it predicted positive. What is false negative? False negative means it's not it is supposed to be positive, but it falsely predict as negative. What is false positive? Is supposed to predict it as negative or no, but it falsely predict as positive. So now you should be able to get what is the total number of actual no's and actual yes, and what is the predicted no value and predicted yes value. So make sure that you are able to calculate this, because you need to use this for the calculation. You need to know the calculation for the accuracy. So this is very, very important. So here our classifier predicts 100. Let's see. Yeah. So we have 165 examples. We have 105 instances of the positive class, total positive class, and 60 instances of the negative class. Classifier managed to predict 100 positive and 50 negative, whereas it predicted 5 as the positive and negative examples incorrectly. I mean, this is the 5 positive, it's supposed to be positive, right? But 5 positive and 10 negative incorrectly. So then we can use these values to measure the performance of the classifier. So this is the formula. This is very, very important for you to actually memorize. The accuracy is you take the true positive plus with the true negative over the total observation. So what was the true positive? True positive was 50, true negative is 50, true positive is 100, true negative is 50, over total observation is 165, right, which is 165. So you get the accuracy of 90.9. So this is how you calculate the accuracy. So this is very, very important, but it's quite simple. If you know how to extract it, it's very, very simple. So an important metric of a classifier is the misclassification or error rate that describe how often the prediction of a classifier is wrong. So if you need the misclassification rate, then you just look at the false positive plus false negative over the total observation. It's just reverse, right? So if you want to calculate as the figure earlier, this is not a figure, 8.2. So the total number of observation is 165, but if you're just looking at a misclassification rate, then you just take the false positive and false negative, which is 9.1. So if you want to generate the confusion matrix, then we can actually use a logistic regression. Remember, logistic regression is actually for categorical, yes or no. So let's import the codes, all the important libraries. So here we are going to use the logistic regression. We are going to create data, then we're going to use the solver deep linear, and we're going to fit the x and y value into the model, and we're going to calculate the confusion matrix CM, and we're going to get the score as well. So we have actually done this before, and we're going to get the accuracy score, right? So this is the actual label, which is 0. This is the actual label, which is 1. So what do you see from here? So this is false, this is true, or this is negative, this is positive. So how many times it able to correctly predict it as negative? So this is true negative, which is 3 times. This is false positive, right? Falsely it actually labels as 1. This is false negative. So this model is quite good. It didn't make any false negative prediction. And the true positive, it managed to get it all correct. So if you want to find the total number of 1 positive is 6, right? 6 plus 0. Total number of negative is 3 plus 1, which is 4. Total number of correctly prediction for the predicted no is 3, and predicted yes, it is 7. So this is how you get this value out. So it gets the accuracy of 0.9, which means out of 10 observations, 9 are correctly predicted with 3 positives and 6 true negatives. There's only one mislabeled observation in our model, misclassify a point from the actual negative as positive. So this is false positive, right? This is false positive. By right, it's supposed to be negative, but it falsely predicted the 0 class as positive. So of course, you can actually extend the confusion matrix to multi-plot. So if you use the iris, you can actually get it also, a confusion matrix for 3 class problem. You can do it for more than 2 classes. So there's now the confusion matrix calculation that is very, very important. And this one is also very, very important, the ROC curve. So this ROC curve is similar to area under curve. Actually, when you actually plot the receiver operating characteristics ROC curve, the area under the curve is what we call as the AUC. So you should be able to explain what ROC curve, and you should be able to draw the plot, right? So ROC is actually a plot that demonstrates the ability of a binary classifier to predict classes when its threshold is varied. So to understand ROC curve, we have to first define what is true positive rate and false positive rate. So this is another important thing. Make sure you know what is true positive rate and also false positive rate. So also very, very important, make sure you know what is true positive rate and what is false positive rate. So the true positive rate is also known as recall, sensitivity or probability of detection measures the proportion of actual positives that are correctly identified. So here the true positive rate means you are looking at the number of true positives that has been predicted correctly over the total number of positives that has been predicted in the model, right? If you look at this point, this is the true positive. So if you want to look at true positive rate, which is also known as recall, the ability for it to recall correctly on the positive rate. So the formula is true positives over total positives, which means true positive, which is 100, over total positive, which is 110. So you can see here the true positive value, and also the total positive is the true positive plus with the false, with the actual positives, my bad. True positive rate, true positives with over the total number of positive, which is 105, my mistake. Total true positive over the total number of positive. So you get this. So 100 over 105. So the ability for it to is 95% for it to be able to recall. So the model is quite good. False positive rate is the probability of a false alarm and can be calculated as the ratio between the number of negative events wrongly categorized as positive, false positive. So as I mentioned, it's very important for you to know the true positive rate and also the false positive rate. So earlier it was, how much, what is the rate of it predicting it correctly. False positive rate is what is the rate that it predicts it wrongly. So it takes the false positive over total negatives. So false positive means here we are actually looking at the false positive, right, which is 10 over the total negatives, which is 60. So 0.17, so 17%. It made a wrong prediction. False positive rate. So make sure that you know what is true positive rate and what is false positive rate. Because these two things is where it will be used to generate the ROC curve. So how do you get the ROC curve? Is that basically when you plot the true positive rate against the false positive rates at various thresholds. So of course, besides the true positive rate and false positive rate, we also have the true negative rate, which is called as a specificity, and that actually measures the portion of the actual negatives that are correctly identified. So just like how you have the true positive rate, we also have the true negative rate, which means how well it actually identifies the negatives correctly. So the formula is the same, true negatives over the total number of negative. So you can see from here, true negative is 50 over the total number of negatives is 60. So you get 83%. And false negative rate is also the same thing. This is how the positive is called as a miss rate, or the chance of probability that a true positive is missed. So it's given as the false negative over the total positive. So you get 4.8%. So it's not that bad. So let me just see here, change some things. So this graph that you see here, the ROC curve, this is very, very important for you to know that you are actually plotting the true positive rate with respect to the false positive rate. So here the graph actually shows the negative and positive classes shown in the blue and also the red. So a black vertical line, which is this one, this is the black vertical line or the dot on the graph. So if we the example on the right hand side of the threshold is predicted as positive, and the example on the left hand side is predicted as negative. So currently the model is plotting is actually giving the vertical line here, because there is a small number of false negative and slightly more on the false positive, right? So it can be observed that if you move this line, you see the green arrow, if you move it towards the left, then what you'll get more positives. More positive also means that you can actually get more false. When you move this line towards here, right, what happened to this graph? You'll get more false positive. On the other hand, if you move this line towards the right, then you'll get more negatives. It also means that you'll get more false negative also. False negative currently now is small, but if you move this line, what happens? The false negative area becomes big. So the optimal value for this threshold is somewhat between these two classes. So that threshold is actually varied. It kept on varied to actually generate this true positive rate and also false positive rate values. And so this point is very important. So you use this threshold value to generate the true false positive and also the false positive rates value. And the ROC curve is generated using these pairs of true positive rates and also false positive rates values. So you need to know these graphs and you need to know how the graph is generated. So if you want to do in Python, then this is the ROC curve. So this code will be given. So basically let me just minimize this. Importing all this value and you're generating two class of data set. You are splitting them for training and you are training the model. You are developing the model and then you're training the model and you are trying to get the values for the probabilities and calculate the scores for these two so that you can actually get this ROC value. So when you try to plot this, what's this? So you get more or less the same. So when you use the logistic regression, you get this area under the curve. So area under the curve means this one, this line, area under the curve. So the more that you're able to get, so if you see here the percentage, when you actually use the logistic regression, you get 90.3%. So which means the logistic regression is quite good. It's able to get. So the blue one is without using any machine learning. So these are the explanations I've already given to you, so I think won't be going through that again. So this is the precision recall curve. So again, it's all based on the precision and also the recall. So this is what we've actually done before. This is for you to actually know. So precision is defined as the number of true positive divided by the number of true positive plus the number of false positive. So which means this one is the true positive, means you get, let me just enlarge this a little bit. True positive is, of course, you get 100 divided by the number of total true positives, which is true positive plus with the false positive. Sorry, yeah, correct. True positive over true positive and false positive. I mean total. So this is known as the precision. So which you calculate this. So recall is the true positive divided by the number of true positive plus. So this recall what we seen earlier, right? So just take note the difference. So don't mix up with recall and precision. So the difference between recall and precision is recall, yes, it takes the true positive, but it takes the total number of positive, which means total number of positive, which is 105, right? But precision means it just takes the true positive with the true positive and also false positive. So which means on your model precision. And then you get this value, which is, so this is recall. So these quantities are also related to the F1 score, which is defined as the harmonic means of precision and recall. So most of the time we don't really use this F1 score, but the F1 score is nothing but a metric of precision and also recall. So the precision of a classifier may or may not decrease with the recall. And lowering the threshold of a classifier may increase the denominator and maybe it will cause more positive to be returned. Now if the threshold was set too high, then of course there will be more positive, which will increase the precision. But if the threshold was too low, then it will actually introduce more false positive. This is what I shown in the graph earlier, right? When you move the vertical line towards the left and right. This is the explanation for it. So these are some of the things. In the recall formula, the denominator does not actually depend on the classifier threshold. So this means that if you lower the classifier threshold, you may increase the recall by increasing the number of true positive results. And of course, if you want to view the relationship between the recall and precision, you can visualize that using the precision recall curve, which is you're plotting the precision on the X and also recall on the Y. So in other words, the PR curve contains this formula value on the x-axis and this formula value on the earlier was y-axis and this is on the x-axis, which nothing but the precision versus the recall. So average precision is just a summary of a PR curve. You just take all the weighted means of precision achieved at every threshold and then you average it out. It's a weighted. So this one is just for fun's sake. You can actually view the positive label or the precision and also the recall rate for you to actually try to plot. So this one I won't be going through. This we have already done it before to try to get the all these metrics. We have already done it before, so you can actually try on your own. So that will be it. So we have actually covered a lot of important points, and hopefully all of you managed to capture the important points.